So the question for us was, how do we study evolving geopolitics globally as it happens in real time? And of course, we wanted to use Spark to do it, so this talk is a bit about our challenge and how we use Spark to achieve this goal. It raised a lot of questions for us. Questions like, how do we use global news as a source of data for like Spark streaming? How do we work at this scale? How do we design patterns architecturally that are deployable and that we can support in production? And then we also had challenges like, what kind of specialist techniques do we have to create to support this use case? And then for global news stories, how do we trace how they evolve over time? And how do we understand how they drift? And this is a use case that isn't just about news. You could use this to trace evolving cyber attacks, evolving policies and documents. So any document collection that exhibits drift over time can be studied using these techniques. So we used a data set that a lot of people use with Spark, usually as training. We used the GDELT. GDELT is very quickly a global news feed. It's published every 15 minutes, and it's a card catalog to the global news. There's about 63,000 news publishing websites globally that are being scraped every 15 minutes and are being pushed through a whole range of analyses and dumped out as part of this index file. It's in 60 languages, so it's global in all languages and from all countries. There are something about 400 to 800,000 articles being published a month, and we wanted to get the raw text for all of that. When we did a quick scan just to find out the NFRs, just to understand the non-functional requirements, right? So how much data are we looking at? We have just quickly here a chart to say like the number of news stories arriving every 15 minutes. And you can see very clearly, if I use the pointer, that there are some spikes up to about 20,000 stories for a 15-minute block on big events. Also, you can see that there's this weekend effect where there's lower news. What this chart tells you, you must remember this, that no one publishes news stories on Saturday night because journalists are drunk. I'm just teasing. But that is what we think is happening, is that no one publishes news on Saturday night. We wrote this book, and this use case is the central theme of this book. This book is not really a book for beginners. It's a book for advanced practitioners who want to learn how to get their science out of maybe laptop environments into big clusters. It teaches you the basics of productionizing and industrializing your science. The guys on the wall, who include me, we have over 65 years of data experience between us building global solutions. Dave and Matt have worked at the 4,000 node Hadoop cluster level, and I've worked on 2,500. I don't know about you.
Worked on kind of big clusters as well. Yeah.
Big clusters, big global solutions, and we put all of our magic, all of our secrets and tricks into this book. And so it's been published since about March, and I would recommend if you like the talk and the kinds of things we've described, that you can go out and buy the book, and it's usually on sale once every couple months from Pact. So how do we approach this global challenge? Well, we needed to source our near real-time URLs. So that means we have to scan this file, right? So we have to go and get it, bring it in, and then scan it. We're going to scrape the article text from sources. It means we need a global web scale scraper. We need to scrape this news, potentially 15 to 20,000 news stories every 15 minutes. There's a deduplication problem. We need to figure out how to get rid of duplicates and old news. We wanted to do dimensionality reductions for some of the science, and to do that, we ended up using random indexing, which is quite an advanced function that you wouldn't learn about in like intro courses. We also use streaming k-means, to build up our top stories. And we're going to talk a little bit about some of the tricks that we use in that process to make sure that we have kind of a rudder to the drifting storylines that we examine. And we're also going to do, the last study is around story mutation. How do we understand how geopolitical stuff happening in the wild is evolving over time? And then how do we visualize and interpret some of that analysis? So this is the general architecture of our pipeline. I'm going to hand it over to Antoine, who wrote most of the code for this book and who open sourced all of it.
Thank you. Thank you, Andrew, for the nice intro. So talking about the stack, the main difference about building batch process and streaming processes is mainly the approach you're taking building your stack. The batch processes can be done, say, top-down. You build your features, or even better, you test your feature before you build them. That's test-driven development. On streaming side, you need usually to build things bottom-up. You need to make sure that your ingestion stack will be robust enough and then can be improved, and then you build features, and then you improve again, and you build your stack this way. So we use Apache NIFI to get all the information we can get from GDELT, ingest that on a 15 minutes window, instead of getting cron jobs that can just be rogue and just get crazy things. So everything properly managed through NIFI, send over to Spark streaming, and lesson learned as part of this exercise is to get a Kafka in the middle that gives us, let's say, a buffer as a flexibility between Apache NIFI and Spark streaming. So now we can get all the news articles published every 15 minutes, 10,000 news articles every 15 minutes, and we can build new features on top of it. So first thing, get the data in, store the data through Spark streaming. Second thing, get all the data in, realize that there are URLs, let's just scrape the web content, get the text content, index the text content in, let's say, Elasticsearch. Do some simple keyword search. Good, we have a monitoring system on global news information. And then what? We get all the text content. Why not looking at the potential duplicates? So why should we care about duplicates? Duplicates may be old news. We want to focus on fresh news. We want the exact time where this breaking news happened, and not that this has been retweeted 2 hours later, or this has been just resold to some news publishing company just a few days later. So we need to be able to get the content the first instance this content has been seen. So we use this SimHash algorithm that we had to create that you can find on our GitHub repo. That's not something you learn at school. That's something you learn on the field. That's something that you need to build, and that's quite powerful. And as you can see, it fits in a dozen lines of code. The concept here is if you need to compare strings, large corpus of documents, you can take a hash and you just can compare the hash with another. But any simple change on the text content, whether it's an additional comma, whether it's an extra word, will result on a different hash, and things cannot be compared. Instead, you will basically generate lots of hashes for all the different tuples or shingles, different words, and aggregate all these hashes in order to build some signatures that describe your document. And then you can compare those signatures and say, both articles are pretty much the same. They only differ by 1 bit out of 32. So we generate all these kind of indexes. We can compare articles together and say, yes, that's near duplicate. Pardon me. But how do you do that at scale? How do you compare each article with each other? We do that through the expand and conquer pattern that we came across, let's say, in the old days of legacy MapReduce. Is instead of having a Cartesian join on all your data, an n-square problem, you expand your problem. You make it even more complex by here 32 times more complex. Because for each, basically my RDD of content, I just generate my SimHash. I expand my RDD to all the possible 32 bits combinations of my SimHash and group all the articles that are not more than 1 bit different. I end up with what? I end up with tuples about article A, article B, and that distance, which is no more than 1. This is a undirected graph that can be easily solved through simple graph analytics. So we end up with groups of articles from 10,000 stories per 15 minutes. We group them into 3,000 unique contents that can be grouped through a simple connected component. So we can wonder what happened to a singleton, let's say a document that is not copied. That could be a kind of fake news. Why not? So something that we did not observe in any other copy of the data set. So once we deduplicate that, we want to deduplicate to remove the noise around GDELT, to get access to true information. The next step, obviously, is to start featureizing all this text content. We want to group things into vectors that we can just send to a machine learning algorithm. Great. Text corpus, first thing, usually term frequency analysis, TF-IDF. You want to reduce the dimensional reduction. We can use PCA. We can feed that in a model. But how can we do that on stream? The context, the problem we have is that we don't know what tomorrow will be. We don't know what words will be used. We don't know what people will be mentioned in news articles. So how can we bind this data set, this feature space, to a fixed dimension that we can track over time? So one technique, for instance, could be to use the hashing mechanism that is provided out of the box by Spark. But if we reduce the dimension through hashing, that can lead to some serious collisions and serious overestimating your model. So instead, we fix the space to a really large, but we fix it with hashing TF, and we use this random indexing technique that we are not really covering in depth here, but there are two articles that you can have a look at. Quite similar to the SimHash problem in a way that you generate random and unique signatures and aggregate all the signatures to embed your large dimension in a lower space. And according to the Johnson-Leidenstrauss, lemma, basically it maintains some distance measure. So the point is now we have hashing, random indexing, stable streaming. We can monitor things as they unfold day by day without having to recreate all the features over time. So we have a consistent streaming. So what do we do with that? I bought myself today a copy of the Irish Times. Good. How many articles do we have a day? I don't know, 50, 100, 200, 300? Good. And how many topics do we have a day? We have K topics. We have the news, local news, we have sports, we have international events, politics, we have K. We believe in K. We believe that the world can only digest no more than K topic at a time. No matter how many articles, we can group articles into K topic. We don't want to classify articles to belong to a topic. We want to group them into a story that can be digested. Naturally, clustering and streaming k-means come into action here. We want to leverage all the nice features of streaming k-means and define our k, number of topics, and the forgetfulness or the decay, or how likely, how far do we want to go in the past, remember the past, observe the current information we have, and drift this story towards the future. How likely this news that we observed 1 hour ago will contribute to the definition of my cluster now. So to give you two examples, for instance, with an infinite decay, we remember all the past. So we are less likely to react to any news article. With a zero decay, we're just swimming in a fishbowl. Don't remember anything, just jump from one story to another one, and you don't have any consistency across time. So, and we let then the cluster drift over time. So I'll leave that back to Andrew.
By not classifying the news into stories like sports or international or property or the things that you might find in that newspaper, but in fact by clustering them, what we're actually doing is creating a dynamic cluster. So we're creating a new kind of newspaper. And this newspaper has sections, and those sections are dynamically generated by the content that we look at. And so if you open up section A, and then tomorrow you open up section A, you don't want to see a radically different set of stories in there. You want some consistency, right, for this A stream. And so what we discovered through using the forgetfulness parameter, and by using a rolling window, that we could use the previous windows to fixate what the main serious topics that you saw over the last window was, and we could allow it to drift in terms of its centroid and content for the new stories. We studied the Paris attacks, and you can see that through using SimHash, we find the earliest instance of the breaking story, and deduplicate and never include anything afterwards that's a repeat. So we have breaking information. That's critical about the SimHash. We then detect, using our clusters, that there is a massive sentiment change amongst one of the clusters. And you can see, if I move that a bit bigger, that at the time of the Paris attacks, our one centroid on this one topic called A, for example, it just shoots up in terms of the volume of stories. So we're able to measure the volume of content within that cluster as a proxy for the world's attention on those topics. We're able to look at the sentiment to find out how people felt about this breaking story. And you can see on the top right that there's a massive drop in sentiment around the time of the Paris attacks on this centroid. So what was really great about this is that over the 15-minute rolling windows, the story changes quite a lot. right? The story changes from something happened to police are investigating to people are in outrage, right? And there's all kinds of condolences coming in. These are all quite different in terms of their hashes, in terms of their words and content, but they're all part of that storyline that's drifting, and this is what the k-means allowed us to do, is to fixate that and allow it to drift over time so we could monitor the situation and the changing sentiment. So we'll move on to the next question, which is how do we then build a social graph or a graph of news stories and watch how they branch and mutate over time and how we can track and trace those? And I'll pass that.
So there is, if you can see in that picture, so basically we can say in this nice purple cluster, it's consistent. Everything is related to Paris attack. But are all Paris attack related articles belonging to that cluster? We see a simple keyword search. Remember that we get all our content as well in Elasticsearch. Good, search for Paris. Exactly 1 hour after the first breaking news happened, I see additional clusters popping up. What that mean here? 1 hour. 1 hour is my half-life decay or streaming k-means. So we stopped talking about news that were not related to Paris. 1 hour later, there is some dying clusters. Spark streaming know that I have a fixed K. Remember, we believe in K. So basically, Spark streaming is trying to recycle dying cluster. What it does, it takes the biggest possible story cluster divided by 2 and create 2 versions of it. And then the second most important, divided by 2, create 2 versions of it. So naturally, we leverage the power of Spark streaming to create branching mechanism. And you end up with what? With a cluster that is about breaking news article, maybe about keep being about the fact, but some different kind of flavor of the same event. So now this one, the yellow one, is about the tributes paid by the politics. The other one is about the social network, the Je suis Charlie hashtag and things, and people reacted to violence towards social network. So that allows us to see that a story may give birth to a different flavor of it, and the more important it becomes, the more it shadows less important stories, and the more it focuses of vision towards a particular event on that day. But how we link them together? All we know that we have multiple clusters talking about Paris, but they are not linked together. They belong into different topics. So to do that, that's our assumption, which is fairly valid, let's say. We predicted all the articles at the time t. Let's just predict them once more time with an updated version of my model. And if most of the articles that belong to this Paris attack cluster now belongs to another cluster, that basically we jump from one bucket to another one. It means that this story may have given rise to this one. And the more articles are jumping from one cluster to another one, the more similar the stories become. So I create a really large cluster. I bring all the same version or different version, but quite similar version of it, and there will be a lot of interconnection of all the articles over time. This is a directed, weighted graph where every story at every point in time in 15 minutes become a node, and all the article you share that is jumping from one bucket to another one becomes our edges. And we can track that as saying, this is our main assumption. The world fits in 15 topics. We cannot digest more than 15 topics at a time. And everything is quite consistent. All the articles at time A are still in the same bucket at time B. Great. But then you get this. You get this Paris attack. You get this disruptive breaking news article that just messing around with the equilibrium. So potentially there is this kind of fragile strings, and you start just pulling those strings and see how the system will react from that shock. What that means is clusters that were quite close, getting related to Paris now, and clusters that were far away are getting more and more different, resulting in this scatter shape. So if you get this equilibrium, you get this shock. Okay, it reacts to the shock. Are we ever getting back to a new equilibrium? Yes. That will depend on what? Potentially the forgetfulness. As an example, we still remember the 9/11 today. It was a long time ago, and it still contributes to our definition of what terrorism is, what violence is. It still contributes in today's newspaper. There may be a mention of 9/11 again. Anyway, so I think that's pretty cool, right?
So I'm a data scientist, and I work at scale, and what we've been showing you guys is how to build a massive geopolitical signals database, a library of signals. Earlier today, we saw one of the talks from Booking.com. They're building a feature database. This is a signals library. So all of us here, we all live on planet Earth, and it's like a fishbowl, it's like an orb. We're all affected by the weather, and that's quite predictive for customer analytics. And we're all affected by the geopolitics, by what's in these newspapers, right? The social mood affects our shopping, our behavior, our choice of holidays, the kinds of things we buy at the shops. This isn't just a toy example that says, oh yeah, there's some great impact and we can study news. This is a mechanism for using a global monitoring infrastructure to create signals that we think boil down into features, and the features can be used in all kinds of science. So the question is, what could we predict and how could we act now that we've created a mechanism for stable geopolitical signals that feed data scientists? So every single one of you guys in the room has a timestamp on something, right? And you can go and look up what the state is on this geopolitical feature database. And these are predictive signals. And they're spatial, they're global, there's loads of information within them, but we've reduced all that complexity down to random indexing so that it's easy to fold them into all kinds of predictive models. And we've been getting reports from the Texata competition where Antoine is helping to organize the competition there about people having great success in predicting riots several months in advance and predicting social unrest, right? So these are actually interesting use cases for a lot of other things as well. We also think that if you were to repurpose these tools and look at other kinds of collections of documents, I've recently been asked to look at millions of policy legal documents and understand how the insurance claim policies have been mutating over time as salesmen copy and paste them forward, right? So there's loads of really practical but a little bit less interesting use cases for this type of technology and this type of work. Just a point about the code. The random indexing piece that we put together was based on another library, but we describe how it works in our book. There are quite a lot of interesting things that we included in our code base, like the code needed to use Goose to build your own web scraper using Spark. Could be very useful. You could scan any kind of stream that has URIs or URLs to go and do that fetching. And all of the tools that we use to do the SimHash and other types of reductions in k-means are available on the website there.
Not necessarily limited to that particular use case as well. Yeah. As we've said, we have multiple different use cases, and whether it is community detection on really, really large graph, yes, it's worth, okay, we wrote it, but it's worth having a look at. It's really...
So we finished a little early, but maybe there might be questions from the audience.
Yeah, first, let's give a round of applause. That was great. It's a really clear explanation, too. I think the breakdown of, like, streaming k-means, it's like original implementation was really cool. But, yeah, any questions about this? Go ahead.
I was just wondering whether you have used just LDA for the topic detection, or have you tried things like NMF, for example? Non-negative matrix factorization?
Not the latter. But yes,
okay.
Doing LDA, I did this one more offline analysis, trying to understand, now that I had all my clusters, all the news articles, trying to understand what the article were about.
And what's the performance of LDA on all this bunch of data? Is it good?
We were not looking at LDA across the entire GTL data set, but on 15 minutes window, let's say, or 15 minutes plus what we want to remember from the past. So basically in a 1 hour window, it's about 60K, 100K records of web articles. So
Yeah,
you.
but there's about 100,000 news stories, but you're right, there is the fetch to go get all the news, and so there's latencies with all the URL crawling. Then there's all of the processing to pre-process that text, right, to feed it into the vector creator. Then we had the SimHash deduplication challenge, which could be a Cartesian join, but is actually reduced to n times 32, right, because we've done the SimHash is scalable as well. So we're able to keep up with our 15-minute window with fairly modest hardware. So we're unfunded. So I actually have a Hadoop cluster in my shed. There's 3 big machines. It's got 180 gig of RAM. Well, no, 380 gig of RAM. And it's keeping up. So, and that's at home.
We also leave that open for interpretation. I mean, get the code, get all the news article, you get all the tools you need to just monitor that 24/7. But obviously, we could not, for financial reasons, to keep that cluster running 24/7 over the past 3 years.
Just to keep in mind, that we hear a lot about dimensionality reduction, but actually the SimHash, that was not just about identifying breaking stories, but it's about volume reduction, right? So it's a performance trick. In addition, we had further vector reductions using the random indexing, right, so that we could reduce the complexity and overhead of running the k-means in real time. So yeah, the whole methodology is geared up around performance.
Thank you.
It's a cool little tidbit about your little shed data center, too.
Yeah.
Yeah, go ahead.
Hi, I found this extremely interesting, given this can be seen as a signal processing library. I was wondering if anyone has been trying to couple this with social media sort of structures, and especially targeting computational propaganda signals, or more specifically, the EU call recently against hate speech. Do you have any thoughts on that, especially in reference to the Memorandum of Understanding signed by the IT companies with the European Union?
That is a really, really good point. Not on this one, but we worked on mashing GDAL data with Twitter data and look at anytime you tweet an article, I know more about this article because you bring me context. So I know what hashtag you use. And I know what article it is and all the metadata and all this processing because I know the GDAL article. So I'm able now to attach some context. I understand what you're talking about. And we get all the news article that we can track. So that's definitely, that's a no-brainer.
In Twitter, you also have the tweet anatomy that not only talks about retweets, but like reply tweets and quoted reply tweets, where you can possibly tag the diversion of, say, after the French attacks into the anti-Islamic hate and the sort of ultra-nationalist hate, because the Twitter signals give you that. You see what I mean?
In other chapters, because this is one chapter of our book, and this is quite a long book. So there's another chapter that's all dedicated to how we did an analysis of Brexit. Okay, so there's also the GeoGChem section that I put together where we mapped out sentiment. There's 4,500 sentiments delivered by the GDAL, and one of them is hate speech. Another one is around immigration, and we were able to cast that information into maps and then demonstrate how to map those up and to look at heat maps. Interestingly, when we looked at immigration, there was a really negative tone around immigration here in Dublin about February 2012, something like that. I don't know what that was all about. There was some incident in the news that drove that. So I think that we have broached some of the other areas of the book to look at that, but if we had the SimHash identifier, right, then you could easily search for quoted news stories in URIs that you were scraping off of Twitter and use those as the keys to join stories with audience, and that would be very interesting.
Thanks.
Yeah. Any other questions? So this was a talk not so much about how, but why with Spark, and we're really excited about the new features in Spark, and hopefully we'll update this, and please let us know if you have any comments.
In the first stage, you said that you eliminate duplicates through SimHash, right? But do you take into account the number of duplicates for a story? I mean, do you give a greater weight to that story or not?
So we had a long talk this morning, actually, just about the kind of questions we get about SimHash. So here's really worrying. A very important story has a count of 1, right? And it's not corroborated by Bloomberg or Reuters or AP, right? And it's not in any of the mainline press. There's a good chance it might be fake news. So we use the first instance and the first timestamp of the SimHash as the time of the breakingness of that story. But if we were to worry about really fake news and accommodating some solution for that, what we could do is we could track that SimHash without adding it to the k-means, and track it until one of the duplicates for that story comes in from a bona fide source we do trust, like a Reuters or a Bloomberg or an AP or the Times, the Irish Times, or somewhere credible. And in that case, we then feed it into that block of the k-means. So it is possible to use the timing of those duplicates, right, to do a lot of fancy analysis. I mean, we've just demoed the basic techniques.
And another question, if when you cluster the articles, if you try to apply other NLP techniques, like try to tag for example, some entities or not? And if
yes, short story, yes, for a different use case. So how you apply NLP extraction from all the corpus documents you get. We can get that fairly easily with libraries nowadays, so whether it's to get all the Stanford out-of-the-box NLP libraries into a Spark job, although we need to be careful about the amount of memory you need to allocate to all the executors. That's not something we're doing for this particular use case. The beauty of GDELT is it comes with all the heavy lifting or all the NLP extraction, the theme extraction, the tone, the sentiment, but it does not contain text content. So we enrich it with the text content, but we didn't want really to overload our model for things that we get for free from this data set. But we used it for a different purpose.
All right, with that, we'll close this one out. Let's give them another round of applause.